Hello students, welcome back. Today we are going to talk about a few problems on the phase equilibrium. This is the topic and I will be discussing both conceptual as well as numerical problems. So, let us start by reviewing a typical phase diagram of a pure substance. So, the number of components that I have in my system of interest is 1. Now, I know from the phase rule that the number of degrees of freedom to describe any system is dependent on the number of components present in the system, the number of phases present in the system, and the relation is f, that is the number of parameters that can be varied independently to describe the thermodynamic state of the system, that is f. So, f is equal to c minus p plus 2. So, this is a phase rule that you have seen before, and f obviously depends on c, which is the number of components, p the number of phases, and there is plus 2. So, quickly let us look back and see what happens if I am looking into the typical phase diagram of a pure substance. So, this is a typical phase diagram and I have chosen certain state points to highlight over here, but simply because it is a one component system, then for a pure substance I must be having C equal to 1. Therefore, the number of degrees of freedom to describe this system will be now given as 3 minus p. Where did I get this equation from? I just use C equal to 1 over here. So, I obtained f, the number of degrees of freedom, that is equal to 3 minus p. Now, as I said that I am going to choose a few representative state points on the phase diagram. The first one is this. This is the green point that is present over here, and I find that here the number of phases is equal to 1. So, p is equal to 1. So, 3 minus 1, that is equal to 2. So, for any portion in this light yellow color region, I understand that there is a single phase of the substance present, and this single phase is the gas phase. Okay? Therefore, it does not matter what you fix the temperature of the gas to be. If the pressure is in any of these regions, the yellow regions that I am showing here, then the system will be stable in a single phase. Now, let us say that I am trying to change the data points, the state of the system along this red dashed line. Now, this red dashed line is a horizontal line which is parallel to the x axis. As a result, the change in state that I am talking about is obviously an isobaric process that I am talking about. Now, if I am somewhere here, then what do I get? I get and experimentally I get a point where the solid and the liquid phases are coexisting in equilibrium. Okay? So, in that case what I find is how many phases are there? There are 2 phases. So, p is equal to 2 at this point. So, f is equal to 3 minus 2, that is equal to 1. And that means that at this point there is only 1 degree of freedom of the system, which basically says that if I fix my pressure here, the temperature at which the 2 phases can coexist in equilibrium has a definite value as corresponding to the point shown here. Okay. So, I either fix the temperature or I fix the pressure, and depending on that I will get the condition under which the 2 phases will coexist in equilibrium. Now, let us have a look at this yellow point. This yellow point is present within this blue region, which is indicative of the presence of one single phase, which is the liquid phase. Okay? And here therefore, p is equal to 1. So, just like the green point, here again at the yellow point I have P equal to 1, and correspondingly I find that F is equal to 2, and I say that as long as I am in the range within this blue region, I can change the temperature and the pressure simultaneously, but still the system will remain in a single pure liquid phase. Now, what about this point, this light blue point that I have shown here, and here again what I am doing is, if I want to go from the yellow point to the green point, I find that it is at this point that there will be a vaporization in the forward direction in going from yellow to green, and condensation if I come from green to yellow. At this point there will be a coexistence of the liquid and the gas phase in equilibrium. So, once again there is this particular point which is lying on the line which is AB, and at this point, along this line I have F is equal to 1. That means that if you fix the pressure, it is at this temperature that you will see the vaporization condensation equilibrium, so that the liquid phase and the vapor and the gas phase will be in equilibrium with each other. Similarly, if you look at the point, this particular green point in the solid phase, once again following the same logic, we will have F equal to 2, and therefore, independent of which temperature and pressure you are using in this range, you will always have a stable solid phase. Now comes one very special point, and that point is the triple point. Okay, this has been shown as a red curve here, red point here, and this is the special point in the phase diagram where the solid, liquid and the gas, they coexist in equilibrium. Okay. So, how many phases do we have here? We have 3 phases, and therefore, F is equal to 3 minus 3, that is equal to 0. And this basically means that this particular point is an invariant constant point where this unique phenomenon of having the solid in equilibrium with both the liquid and the gas phase will occur. And the triple point is therefore, for the pure substance such as the one that I have shown here, is an invariant point because it does not have any degree of freedom. Now, moving on from here, let us review a typical phase diagram of a binary mixture. So, what do I have? I have started by preparing a liquid mixture having the component A shown here by the yellow circles and a component B shown here by the green circles. Okay. But please remember that both the components A and B are volatile. As a result, if I keep them in keep the liquid mixture in a sealed vial like this, there will be evaporation from the liquid phase to the, and forming a vapor phase. So, what will be there in the vapor phase? As I said, both component A and B are volatile. Therefore, the vapor phase will also have both the components A and B as shown in this picture. Now, for a binary mixture in a situation like this, where I have both the liquid mixture and the vapor mixture is coexisting in equilibrium, then I must understand that here the number of components is equal to 2, and it happens all throughout the vial irrespective of whether I have the liquid mixture or the vapor mixture of A and B. Now, what happens here is I understand that there are 2 phases here, unlike the case where I was talking about a pure substance. Now, I have 2 phases in equilibrium where I simultaneously have the components present in the vapor phase and the liquid phase. Both the components are present in both the phases. Therefore, if I want to calculate the number of degrees of freedom, then I would say that F is equal to C minus P plus 2. So, here C is equal to 2. So, I have put 2 here minus P, which is 2 here, and then plus 2. So, what is the result? The result is 2. So, in this case, I will have 2 degrees of freedom. Now, I already know that for this equilibrium to be maintained between the liquid and the vapor phase, then I must be having this condition met, that is, the chemical potential of the component A all throughout the sample at a given temperature and pressure must be constant, which means mu of A in the liquid phase at the given temperature and pressure must be equal to mu of A in the vapor pressure under the vapor phase under the same condition of temperature and pressure. But is it valid only for A? No, it is also valid for the component B. Therefore, under the given condition of temperature and pressure, the chemical potential of B in the liquid phase must be equal to the chemical potential of B in the vapor phase. So, this is what we have learned so far. Then the question is, what are going to be those 2 independent variables to describe the equilibrium? And that is exactly what we choose when we draw the phase diagram of this binary mixture. Okay, so what are the independent variables that I will choose to describe the phase equilibrium? The first one, of course, is temperature. We can fix the temperature in the laboratory very easily by using a thermostat. What would be the second one? A very convenient choice is the composition of the liquid mixture. Now, how many variables do I require to describe the composition of the liquid mixture? I would say only one, and that is because, as you understand, the liquid mixture will be characterized by the mole fraction of the component that I have chosen to describe its composition. So, here let me choose the component A. So, X A is the mole fraction of the component A in the liquid phase. You can very easily say that, well, do not I need to specify what X B is? The answer is no, and that is because X A plus X B by definition is equal to 1, and therefore, X B is equal to 1 minus X A. Therefore, if you define what X A is for your liquid mixture, then automatically X B is fixed. So, what is the experiment that you are going to do? At a given temperature, you are going to prepare one solution having the mole fraction of component A as X A. Then you are going to prepare another solution having some other values of X A. So, this way you can prepare many different solutions for the values of X A going from 0 to 1. Okay. Now, with these solutions you are going to measure the properties. Now, which property will you measure? You will measure the property of the total vapor pressure of the system. Okay. And the outcome of your experiment would be an diagram like this. As you see that when the mole fraction of A is 0, then the total vapor pressure that you see is coming entirely from the component B, because in the liquid phase your X A equal to 0 means it is X B equal to 1, that is pure component B, and therefore, the total vapor pressure that you see for this solution can be attributed to the vapor pressure of that particular component B at a temperature T. Similarly, when I am talking about the X A equal to 1, then I have in the liquid mixture only the component A, and the partial pressure in that case will be, and the total vapor pressure will be that of the pure vapor A. In between, if my vapor mixture follows the Raoult's law, then this is going to be the total vapor pressure will follow a linear plot like this. So, now you understand how the underlying thermodynamic principles actually decide what the phase rule is going to be, and when we look at phase rule, we find out how to design our experiments. Now, moving ahead, I will come back to the consideration of pure substances, and let us talk about the slope of phase coexistence curves. Okay? And our discussion will be based mainly on Clapeyron equation. So, the basic idea is I have, let us say, two phases in equilibrium, and then I am trying to change the temperature of the system by a small amount from T to T plus dt, and I will expect that the two phases will still exist in equilibrium, and therefore, I will see that it will require me to change the pressure by dP. And then we ask the question, what is dP dt? That we have shown is related to the change in entropy during the transition divided by change in volume associated with the phase transition. Okay? Now, if I focus definitely on the liquid solid phase coexistence line, then I am talking about this line A D. And then I would like to say that I can write down the Clapeyron equation that along this solid liquid coexistence line, the dP dt of fusion that is decided by change in entropy of fusion and change in volume on fusion, and the m, these subscripts mean that I am looking at molar values of these two thermodynamic quantities. Now, from the experiments you can find out that for delta S fusion for a given substance is 22 joules per Kelvin per mole, and it is also found out that the change in volume per mole of the for the fusion process is 4 into 10 to the power of minus 6 meter cube per mole. In that case, if these two informations are available to you, you can very easily find out what dP dt is. So, here I have put in the value of delta S and I have put in the value of delta V, and I can directly calculate what dP dt is going to be. So, dP dt I found that it is 5.5 into 10 to the power of 6, then comes the unit that I have derived by simplifying what I have here. So, from the numerator, mole inverse cancels out the mole inverse in the denominator. So, I have what I have here is joules per meter cube per Kelvin. Now, look at what is expected as the unit of this quantity dP dt. I understand that in the denominator I have a temperature. So, I understand why Kelvin inverse is present on the right hand side. Now, I have on the numerator dP. So, I would expect a pressure unit over here. So, what is that conventionally used unit of pressure that appears here? In order to do that, let me do a quick check of the unit. So, 1 joule is nothing but 1 Newton meter. Therefore, 1 joule per meter cube, that is nothing but 1 Newton meter multiplied by meter cube per meter cube. So, the result is 1 Newton per meter square. Therefore, whenever I am writing down 1 joule per meter cube, I am essentially looking at an energy scale or the pressure scale of 1 Newton force per square meter area, and by definition this is nothing but 1 Pascal, and therefore, I would say that this is 5.5 into 10 to the power of 6 Pascal per Kelvin. Therefore, you can immediately go back and say per unit change of temperature in the Kelvin scale in this case, there is a change of pressure which is 5.5 into 10 to the power of 6 Pascal. Okay. So, what is my conclusion? My conclusion is that when I have dP dt fusion equal to this value, the conclusion is that in order to increase the melting point by 1 degree centigrade, I need to increase the pressure on the two phases in equilibrium by 55 atmospheric pressure. So, that is the reason why you see that first of all the slope is positive. Therefore, if you want to increase the equilibrium temperature, you have to increase the equilibrium pressure, and you see that this is a very high value of the slope, which means that I have a steep phase coexistence curve between the solid and the liquid, for which the data of fusion of delta S and delta V are given to you. Now, if I go ahead and consider the liquid vapor phase coexistence line. So, I am looking at the line AB. Along this line, I can rewrite the Clapeyron equation as dP dt now corresponding to vaporization, and that would be decided by the change in entropy, molar entropy divided by the change in molar volume on vaporization. Now, if the data I obtain as delta S is 95 joule per Kelvin per mole and delta V is 2.0 into 10 to the power minus 2 meter cube per mole, then I can easily calculate that dP dt vaporization is 4.75 into 10 to the power minus 2 Pascal per Kelvin. So, I have followed the same numerical exercise that I have done before for the fusion, and this is the result that I get. Now, look at the picture and compare the AD line with the AB line. So, at a given point of this vaporization line, that is, I see that dP dt vaporization has a value like this, which when compared to the fusion is a much smaller value. Therefore, my conclusion would be the slope of the liquid vapor coexistence line is much smaller compared to that of the solid liquid coexistence line, and therefore, you have to apply much less change in pressure if you want to change the liquid vapor coexistence temperature, which is the vaporization temperature. Okay. Now, moving ahead, let us have a conceptual problem here, which is very simple actually. So, this is the phase diagram of water, and I want you to find out the temperature in Kelvin and pressure in millimeter of mercury at the triple point of water, given that these two measurements have been done. I have measured the vapor pressure over ice and fitted it to an expression like this as a function of temperature. And then I have also measured the vapor pressure over the water phase and fitted it to a temperature like equation like this as a function of temperature. Then what happens? I understand that at the triple point, let me say that T is equal to T Tp. So, this small Tp corresponds to the triple point. Then I must be having LNP ice equal to LNP water, because it is at the triple point that all three phases coexist in equilibrium, and therefore, I can say that under such condition I can write down that whatever appears on the right hand side of this equation must be equal to whatever appears on the right side of this equation, and this would allow me to calculate do a little bit of algebraic a little bit of algebra, not much, and I can find out the triple point temperature of water in terms of these constants A ice, A water, B ice and B water, which would be determined from the experiment. And then obviously, by knowing these two equations, knowing A ice and B ice, you can go back and find out what the pressure, vapor pressure over ice and water should be from these equations. And if I just look at the phase coexistence curves involving the vapor phase, let me quickly remind you that in this case we assume that the gas phase behaves ideally, and then we have the Clausius-Clapeyron equation. And in that case, instead of writing the Clapeyron equation, we either use the differential form of the Clausius-Clapeyron equation or the integrated form of the Clausius-Clapeyron equation. Okay? So, sometimes there will be a lot of data given to you which may be available to you, like the normal boiling temperature for the solvent benzene that I have shown here, the vapor pressure of liquid benzene, enthalpy of fusion and the vapor pressure over solid benzene at given temperatures. Now, I am going to use this data to find out, let us say, the molar enthalpy of vaporization of benzene. So, where shall I start from? I know that from the integrated form of the Clausius-Clapeyron equation, I can write this particular equation, and then I can plug in the values from here, and I can write down delta H molar vaporization will be given in terms of the temperature at which I have the data on the vapor pressure, which is this temperature, and then all the other quantities are known to me, and I will put in the values over here, and I can find out that the delta H m vaporization is 33.2 kilojoules per mole. There are other things that I can find out. I can determine the molar entropy of vaporization. So, the molar entropy of vaporization can be decided if you know the enthalpy of vaporization and the boiling temperature, and accordingly I will just put in the values of these quantities from the data that I have with me, and the molar entropy of vaporization turns out to be about 94 joule per Kelvin per mole. There are other things which are not so obvious from these data can be determined from here, and that is the molar enthalpy of sublimation. Now, did I give you any information regarding the sublimation? No, but I can find this out just by writing that the molar enthalpy of sublimation by definition is molar enthalpy of the gas minus molar enthalpy of the solid when we have the solid in equilibrium with the gas over it. Now, I am going to use the molar enthalpy of liquid. I am going to subtract it from the gas phase value, and I am going to add it to the solid phase value. Now, what is it that I have found from here? I find that delta H m sublimation is equal to the molar enthalpy of vaporization plus the molar enthalpy of fusion. So, now do I know the molar enthalpy of fusion? Yes, this is something that is given to me. Do I know the molar enthalpy of vaporization? Yes, I have found it out by using these two sets of data. So, I can go ahead and put them together, and I find that the molar enthalpy of sublimation is 43.15 kilojoules per mole. So, this way it is actually possible to talk about the coexistence of phases at certain temperature, pressure, and you can design your experiments to construct the phase diagram and then rationalize the shape and the slope of the phase coexistence lines when you identify them. Thank you.